Okay, good afternoon. Um, okay, sure. So I won't do the summary of summary. You have heard beautiful summaries of the three tracks. So, sorry, what happened? Oh, this doesn't work. Let's see if this works. No, it doesn't work. This doesn't work, so let me try. Yeah, this works. Gave away the what I was going to show next, but anyway. So, since you have heard nice summaries of the three tracks and some of the highlights and some important work that was presented at this workshop, I'm only going to make some broad remarks and maybe just highlight some of the topics. ACAT 2017 in beautiful Seattle. We should thank Garden for bringing ACAT to the United States after 17 years, and this has been really awesome. It's always nice to come to Seattle or Vancouver. And of course, ACAT 2017 also brought with it the Great American Eclipse. Of course, this was ordained to happen before we decided on ACAT, and we didn't have any priority. So I saw nice pictures of everybody, looking at the partial eclipse. I, for one, since I had witnessed a total solar eclipse before, you sort of get, addicted to it. So I had to go to Nashville to see the total solar eclipse, and that kind of the logistics caused sleep deprivation for the rest of the week, but still, it was worth it. It was just awesome. So that was I think must have been an exciting beginning for the workshop here. So the ACAT workshop series, as you all now know, has the three major tracks: computing technology for physics research, which deals with languages, software, distributed and parallel computing architecture, visualization, and so on. And then there is the track 2, data analysis, algorithms, and tools. And now it's getting, of course, overwhelmed with machine learning, as you noticed. Track 3 is computations in theoretical physics, and we have just heard nice summaries of all of those tracks. So the ACAT workshop series, I just wanted to say something about the ACAT workshops in general and make some, tell you something about the history of, at least in the recent past. If Denny Peregali, who couldn't be here, who was I think the initiator of this series back in 1990, he always used to show something like this. This, I think, is from his one of his slides, that the main reason for ACAT is bridging disciplines between theory, computing, and experiment, and bringing communities together, bridging communities. So the history, you have already heard about the Aztec feather sheet, so I'm not going to mention that again. So this started in 1990 as AIHENP workshop. Now tell me, is ACAT better than AIHENP or not? I mean, so it was artificial intelligence in high energy and nuclear physics, first held in Lyon, France, and then it was held in 1992, 95, 96, and 1999 in those places. So then in 1999, of course, we offered to have the workshop in the US at Fermilab, and that's how after 1999 it became ACAT. So some of the early pioneers of AIHENP, as I said, were Denny Peregali, René Brun, Bruce Denby, and so on. I think maybe there was Dmitry Sherkov, who passed away recently, who was also very much involved in ACAT 2000 from Russia. Christian Kiesling, Leif Lundblad, Carsten Peterson. The ones I've shown as NN in the parenthesis, they were the AI people, the neural networks people. Bruce Denby was at Fermilab at CDF, and then Leif Lundblad and Carsten Peterson actually wrote the JetNet package, which became one of the important startup packages for many of us starting on neural networks in HEP. Christian Kiesling had done neural networks in online triggers at Hera. So the artificial intelligence, this team actually was very much excited about it, and that's how this series had AI as one of the important aspects. So when it came to when we tried to organize it in the U.S., it had three tracks as you have seen. It's not just artificial intelligence, not just neural networks, and so. In those days, multivariate analysis methods were not that much appreciated. There was a lot of resistance, and so we used to call it advanced analysis methods. And then, of course, computing, we always try to do advanced computing. You're always you want to be at the bleeding edge or the cutting edge, advancing the field. And so we thought, okay, AI, HENP is a mouthful, and so we can combine the advanced computing and advanced analysis methods. And so we said advanced computing and analysis techniques in physics research. Why stop at high energy and nuclear physics? So we broadened it into physics research, and that's how it became ACAT. We said, well, we are changing the name anyway, so why don't we see if we want to change the logo? And so we were thinking about what could be an interesting logo, and then I saw this picture of Feynman when I was looking at the previous visionaries about artificial intelligence and the neural networks. I found out that Feynman actually worked one summer at Thinking Machines just to be close to his son, who was at MIT at that time. So he went over to Boston and then became more or less like a consultant at Thinking Machines. And he worked on so-called the connection machine that he helped design. And so he wore this thing I don't remember what was the occasion, but anyway, so then that inspired the ACAT logo. So we thought maybe we will do something like that for ACAT. But then International Advisory Committee, of course, had a very sentimental attachment to the Aztec feather shield. So at that time, we used both of them and said, okay, next time, whoever organizes it can decide what they want to do. So ACAT 2000 was held at Fermilab during October of 2000. And you can actually check out some of the videos of the plenary talks then. It might be interesting to see what people were saying at that conference 17 years ago. And we had some really heavyweights, some VIPs in various aspects of the workshop. We had Bjarne Strostrup, who's the father of C++. And in fact, that's when actually we initiated HEP, especially Fermilab representation on International C++ Standards Committee, because we were in the process of migrating from Fortran to C++ at the Tevatron and CDF and D0 experiments. Ian Foster, of course, who is known as the father of the grid, was conveniently down the street at Argonne, so we got Ian Foster to come and give us some momentum to the grid partnerships. Grid was in its infancy, I think, at that time, and so that was a very good connection. Stephen Wolfram came and talked about cellular automata and all that. We had John Moody, who was working on machine learning, Alex Allain, Robert Ryan on large-scale simulations, and of course, René Brun, who was on the International Advisory Committee, was there. And in fact, it was at this meeting, I think, he really got passionate about launching TMVA, implementing multivariate analysis methods in root. And so TMVA, I think, was born at this 2000 workshop, ACAT workshop. So since then, ACAT has been held at all these different places. So you can see, it has gone around quite a bit around the world to Russia, Japan, Germany, Netherlands, Italy, India, UK, China, Czech Republic, and the last one was in Chile. And each time ACAT had tried to have a special focus topic. So here are the special topics that Denny used to show, and I just added a couple of them. Quantum computing back in 2007. In fact, even in 2000, we talked about quantum computing and where they might be applicable. And of course, in ACAT 2017, we have Back to AI Reloaded, the 18th edition, and it was nice to see that Gordon added his own little logo to the Aztec logo, so that I don't have to feel guilty for for my logo from 2000. So now coming to ACAT 2017. There have been about 200 participants, 24 plenary talks. We had 4 very interesting roundtable discussions, 86 parallel session talks, and 69 posters. I don't know if I got all the numbers really correct, but so it's a very good size meeting, and has been very, very nice. A lot of very interesting talks and interactions. So let me just give you some impressions on the highlights of ACAT 2017. Since you have heard all the summary, I don't want to keep you again going over various things. So for track 1, I just put down some of the topics, the heterogeneous architectures, which you just heard about, use of GPUs and FPGAs and so on in computing, and we need to have software that could adapt to these heterogeneous architectures, hardwares that we can have, and there has been a lot of very interesting discussions. Many data preservation projects are going on at Tevatron and LHC, definitely, especially the LHC data. So we have heard from INFN, CNAF project, and the Tevatron LHC on online systems and triggers. And containers have been rising in importance. That there was discussion on for software development, deployment, how important these are, and for portability and scalability. And then the interesting thing that I find is that now machine learning has been creeping into the other tracks as well. So it was nice to see machine learning tools, also actually prominently show up in the other 2 tracks. In this case, for fast simulations, as you just heard and saw the fast simulations. For G&V, and then the Atlas calorimeter simulations. And HEP visualization, of course, is always an important thing. For track, I will talk about track 2 later, because that's about machine learning, which was the focus of this conference. Track 3, also you've heard that there have been new developments in methods for symbolic calculations, loop integrals, and nice that the Loopedia, there's a new database for these loop integrals. There have been developments and optimizations of generators, improvements for improving the precisions of calculations as well as making them quicker. New language, Go for concurrent programming, roundtable, which are analytical versus numerical methods. And again here, machine learning in theoretical physics, PDFs to MC tools, possible machine learning to accelerate lattice QCD calculations. So it's interesting to see, again, in track 3, in computations for theoretical physics, there are important advances in possible machine learning applications. So let me show a few things about the track 2, data analysis and algorithms and tools. And of course, it was predominantly machine learning algorithms such as the neural networks, BDTs, and many flavors of DNN. Applications in all sorts of things. Actually, I had been, those of us who have been proponents of this for decades have been saying that in every aspect of data reconstruction and data processing, we would want to use these machine learning algorithms, and that is actually coming to fruition now. And end-to-end event reconstruction, which basically going from physics-based variables now using all the raw data input to have image kind of recognition for the whole event. These are some of the examples, and you have already seen them, so let me not go through that. So, so I just wanted to say a few words on machine learning. Machine learning is simply put is a paradigm for automated learning from data using computer algorithms. And it requires little a priori information about the function to be learned, And it's a method that can approximate a continuous nonlinear function to arbitrary accuracy, and it's called a universal approximator. And there is strong mathematical, statistical underpinnings for these methods, and so I think these are very robust and well and can be understood in a statistical analysis. So over the past 3 decades, multivariate analysis methods have gained gradual acceptance in HEP, and now they are state of the art. Some of the most important physics results in HEP have come from the use of these methods. In 1990s, I would say in the title of on my title slide, we are riding the wave of the future, and now the future is here, and these methods keep growing in importance, and they will be much more important as we get more data and as we approach more complex and challenging situations. So just to look at what the trends have been, in 1990, the proponents and practitioners were kind of on the fringes of the community outside the mainstream. And then for a decade, there was a struggle for acceptance by the HEP community, and there were some early work at Lab Tevatron, et cetera, using some of these simpler software tools. And in 2000, the multivariate methods and machine learning got more accepted. By 2010, these had become ubiquitous. Everywhere we were using these. But now I think at 2017, we are, machine learning is on steroids, I think. So the buzz about deep learning is that, you can have multi-scale feature learning with multiple hidden layers. Each high-level layer learns increasingly higher-level features in the data. You can pre-train initial hidden layers with unsupervised learning. And as I said, you can use raw data inputs instead of derived intelligent variables. So that's one of the attraction, or you can use both. And final learning, of course, can be better, as we have seen from many examples, as compared to shallow networks, particularly if you can provide it inputs with unprocessed raw variables. However, you need a lot of processing power, and so GPUs are the hardware that one would use. A lot of training data, although now we create lots of Monte Carlo, we have lots of data, but there is never enough Monte Carlo. But the other interesting development in the recent years is that you can also generate limitless data by small perturbation of the generated data, which has been shown in machine learning, image recognition applications very nicely. And so this actually is a very nice thing. I'm going to skip this because you have seen many of those. So there are, of course, many flavors of DNNs. Deep feed-forward, fully connected ones, convolutional ones, recurrent, adversarial, and they're being used for all sorts of things. And as we have seen in a couple of examples, the resources and the complexity may not be required and not justified probably in every case. And so we are back to the problem of finding the right method for the right application. So I just wanted to show that science. I don't know if you've seen this. Had a nice issue. AI transforms science, and it talks about. This is the 7th July edition. Talks about all the different sciences. From genomics, biology, chemistry. All sorts of sciences that are actually using this, using AI. So we are not alone in this domain, And they had a small, Adrian Cho actually wanted to write something on how it's being used in LHC for new particle searches. And so, he talked to me for an hour and actually wrote a small thing. AI is certainly proving ground the hunt for new particles as an insert in one of those pages. So I want to just end with saying that the prospects are great. We have these very advanced techniques and tools in our hands, but the stakes are also very high. Until the standard model was incomplete, we were looking for the next quark. We were looking for the missing link, the Higgs boson, Even though we did not actually think that we will actually find this scalar particle, we found it. And so in some sense, you can say that the discoveries were sort of guaranteed until then, but now there are no more such guarantees, right? And any new physics, the stakes are really very high as we try to discover, new profound principles of nature beyond the standard model. And so the bar for discoveries have to be very high. So I just want to caution that therefore machine learning community has a serious responsibility, because we are actually the proponents and developers and validators of these methods, and we try to keep pushing the envelope, and so I think this is something that we have to take seriously. So some impressions of this meeting. I think it was amazing to see a diverse array of topics and applications, a variety of studies and applications presented. There were excellent presentations and posters. As Sergey mentioned, 13 collaborations were represented. And it's also great to see many new faces, and especially lots of passionate, very smart, talented young people. ACAT, this edition has provided a very friendly atmosphere for a productive meeting, I think. Lots of food and food for thought as well, and inspiration for action. So I thought, maybe we could in the future maybe also reach out to some of the other, related physics fields. Accelerated physics, I know, has been now beginning to use machine learning in accelerator controls and maybe in design optimizations and things like that. So that's something that they might benefit from coming to ACAT meetings. Large-scale accelerator simulations, of course, we have seen that that could be an interesting thing for them to with this meeting as well. Astrophysics has already many applications, astrophysics and cosmology with machine learning. So that's something, again, we could reach out to, have plenary talks and parallel session contributions. I think it would be very useful for the machine learning community to interact with statisticians, so that, we have a better, robust understanding of things, of the analysis trail. And then we can think of, as I said, there are many disciplines that are now into machine learning, and so it should be very interesting to connect to those communities. So I want to end with saying that the future prospects are that we have lots of challenges, exciting prospects for awesome discoveries, and so we develop the tools and skills to unravel the mysteries of the universe. So I want to say big thanks to the Scientific Program Committee, which put together such a wonderful program chaired by Federico, and he also had lots of IAC meetings, which helped to bring the program together. And my apologies that I have missed most of those, but some of you actually really worked very hard to bring this program together. And also I want to thank all the track coordinators who had to work very, very hard to make sure that the program is diverse and appropriately put them in various boxes and sessions and so on. I want to also thank the International Advisory Committee that is listed here. And huge thanks to Gordon Watts, who has been very passionate, and he pulled pulled together a great and wonderful conference. And also thank Shichi Shu for the co-chair of the conference. And last but not least, all speakers and attendees and participants. Thank you all. Let's look forward to the next ACAT. Thank you.